Hello everybody, it's a great pleasure to introduce our today's speaker, Rudolf Sollacher. Dr. Sollacher did his studies in physics at the Technical University in Munich and got his PhD there on quite a different topic, on quantum field theory, if I'm right. And after that he went for some postdoc stays at the Niels Bohr Institute in Copenhagen and at the what's the English name for it? Institute for Heavy Ion Physics in Darmstadt. Although he left 1 year before I arrived, so we didn't have overlap in Darmstadt. After that, already in 1996, he joined Siemens Corporate Technologies. One needs to know Siemens Corporate Technologies is the central research unit of Siemens. I think they call it being considered the think tank of Siemens. And for the last 15 years he has been working with Siemens Corporate Technologies on a variety of topics which are also of interest for us. He started with traffic control systems and traffic modeling. He's been working a lot on sensor networks, wireless sensor networks, machine learning, neural networks, and I think the latest subject which entered was the power grids. And today he's going to give us some overview of his recent activities, also related to the sensor networks and probably the other newest topics as well. We're very happy to have you here. The floor is yours.
So thank you very much for this invitation, for the opportunity to give this presentation. I had already seen some presentations of the labs and I found this very inspiring. I think now it's my turn to give you some information from my side. So I decided to basically start with a short introduction to Siemens research and related activities to give you an idea what is happening in the industry, at least in our company. Then I will give you some overview on wireless sensor networks, why they are an interesting technology and what are the challenges associated with them. And in the last part I will provide you some information on some research which I did some time ago with a PhD student on recurrent neural networks, especially useful for using embedded systems. Okay, but now let me start with some overview on activities at Siemens. So, what Siemens is a huge company with more than 400,000 employees worldwide, and as such covers quite some application fields. Here you see some examples of innovations at Siemens, going from light-emitting diodes done at Osram, so high-speed trains, solar thermal power plants, turbines, electric cars, digital revenues respectively, virtual reality applications, so biosensors or healthcare solutions. But this is just some examples, not a complete some numbers to start with. So Siemens altogether has a budget, R&D budget of roughly 4 billion euros, corresponding to about 5% of the revenue. This covers all the activities with some 30,000 R&D employees worldwide. Now, one has to distinguish what this means, because Siemens has 4 business sectors: energy, industry, healthcare, and since October a 4th one called infrastructure and cities. I will later show you or give you a few hints why this fourth sector has been introduced. And the large majority of these R&D employees are actually in these business sectors, and work on pretty product-related research topics. In addition, there is, as already mentioned by Fischer, a central research and development unit called Corporate Technology. This is where I'm in. And this unit has about roughly 1,500 employees. So this is only the smaller part, but nevertheless a very active one. So it's just for curiosity, some numbers. So there are 18,000 software engineers, and according to the information I have, Siemens is producing more software than, for example, Microsoft. Now, corporate technology is not just located in Germany. So we have the main locations are Munich, Erlangen, and to some extent also Berlin. But there are also places where Siemens is active. In the USA, there's a location in Princeton and in Berkeley. In Russia, in Moscow and St. Petersburg. We've started some locations in Asia as well, as you can see. And then we have, of course, a couple of, or quite a lot actually, of cooperations with other institutes. Well, can get some glimpse here where these are located, but this is, of course, not a complete overview. Now the business of Siemens, and in particular the innovations, are guided by what has been by so-called megatrends which have been identified and which require some answers. And these are, first of all, urbanization. So this means that there is a current trend in cities that even more people are living in cities. And there are, of course, some challenges associated with this concerning supply, logistics, security, and so on. And to give you an idea why, so for example, Tokyo provides 30% of Japan's gross domestic product. Similarly for Paris and France. So this is the reason why it makes sense to focus on it. And this is also one of the reasons why this fourth business sector has been created at Siemens. And we have demographic change. So we will probably get older than previous generations, at least in average. And this also implies some solutions. I mean, how to keep us more healthy, how to support life if you cannot do all the activities which you can do when you're young. This deserves answers. Of course, very important is also climate change, which implies that we have to solve, to reduce energy consumption, or at least increase the amount of clean energy or renewable energy in our supply mix. And last but not least, globalization. The consequences of globalization is that the global trade has increased dramatically within the last roughly half century. And to give you another number, the freight volume, the ocean freight volume, has increased over the last 40 years by a factor of 4.5 roughly. Some examples where Siemens is actively doing research and innovation. You probably all know this Decentralized initiative, where huge solar power plants shall be installed in North Africa to provide part of Europe's energy demand, and of course also the African one. In addition, there are related activities concerning, for example, the smart grid. We currently are facing more and more problems with, in particular, in the distribution networks for several reasons. First of all, the traditional, when these were created, you basically had an energy flow from the transmission grid towards the consumers. So basically, in the distribution grid, energy is flowing from the grid to the consumers, and this made the engineering of these systems pretty simple. You only had to care for some capacity limits, and that's basically all. Now, with these renewable energies, which are basically the decentralized generation plants, you suddenly have the situation that you're producing energy, so you have energy flow back into the transmission network in some situations. And as these distribution networks basically have almost no sensorics installed and basically very little control implemented, we are more and more running into problems concerning the stability of these grids. For example, frequency stability, which has to operate on very narrow limits, or voltage control. Now, related to this is, for example, electromobility, or another example which is quite different is how do you adapt current products to the requirements in, for example, emerging countries, and there are some solutions concerning computer tomograph, for example. Now, let me come to my first, besides this overview of Siemens technical part on these wireless sensor and actuator networks. To give you an idea where these are useful and rely, I start with some application examples. So let's start with production logistics. So imagine you have some active tags which you attach to goods, materials, components, and whatsoever. So what can you do with this? Well, first of all, of course, you can track these goods. I mean, this is not very new. Sometimes already done with RFID tags, but RFID tags are passive. So you only get the information when you pass a reader, or you have a mobile reader. So by themselves, these tags cannot do anything except maybe measure some quantities and store it for some time. It would, of course, be much more interesting to have this information available on demand, for example, if some locations reached to provide a signal without having a reader infrastructure there. So that's why you would like to have active products and also product tags with a memory. Then another example is product self-diagnosis. So imagine you have these tags attached to some components in, for example, a vehicle. Then if something, if the car is broken for some reasons, then you can easily get the information of the history of these parts and read out, and hopefully improve the diagnosis and repair activities with this information. So also in retail, you can control the quality of these goods, and you can also, for example, trace organic food as just one example, which is helpful for the consumer. Other application examples are in areas navigation, monitoring, and process control. For example, when Siemens is also supporting or building huge plants, for example, for cement production, and typically in the construction phase, the components and pieces of the material are stored in some large areas, which easily can cover an area of 1 square kilometer. And you can imagine that it's not so easy to find the material there, in particular having in mind that the people which are collecting the workers there are not very educated people typically. So you would like to have a solution which helps you finding material. So these active sensor networks or tags can be a solution to support navigation in such a system or searching for certain material and finding it. Other application is the monitoring of machines in plants, for example, or distributed process monitoring when you have a wide, largely extended production process, for example. Well, process monitoring and diagnosis, of course. And finally, also, it's getting more and more interesting to have a self-organized process control, simplifying the engineering and also making the control more robust to, for example, single point of failures. Yeah, and finally, there's also a task of monitoring infrastructures, like here pipelines, for example. You want to detect leaks, or you want to detect some events which could indicate some possible threat on the pipeline, like construction activities which were not planned, or of course some damage, some terrorist attacks, for example. You also would like to monitor the power lines, for example. Currently, there's a limit on the power plants, on these power lines, the capacity limit, which cannot be exceeded. But this is a very conservative one because it assumes worst case conditions, so something like 35 degrees temperature, and this implies that we cannot put too much power flow to this cable. But often the temperature is lower, at least in our not here maybe. As a consequence, you could increase the amount of power transported by these power lines, provided you know the temperature and the temperature of the cable. So these are examples where these wireless sensors, or sensor and actuator networks altogether, could be useful. Now, what means a wireless sensor and actuator network? Well, it consists of sensor nodes, which have the following platform components. You have a sensor module, which carries some sensors. You have a transceiver module for communication, a microprocessor, and an energy supply. I will come to these back on the next slide. Now, how do these communicate? There are typically two major solutions, and of course mixed solutions as well. The one is a star topology, which is basically some kind of master-slave construction. You have one master, and the slaves are communicating directly with this master. This is only suitable for small areas due to this limited wireless transmission range. The solution for extended systems are meshed networks. Here you can you have an impression what this means. Here you have several sensors with limited transmission range. In order to get the data, for example, to here, they are forwarded by other sensors. What is the main benefit of these solutions? Well, first of all, you can avoid this wires. Whoever has tried to set up a system of many components, simply considering the power supply, definitely has been annoyed at least once by this kind of wiring problems. Also in industry, actually it happens quite often that these wires get damaged by accident. That, for example, a truck hits one of these cables and destroys it. So this, as such, is also useful to have it. I'm sorry, I forgot the other point. We of course get also additional information from this wireless sensor networks. A very prominent example is due to the fact that we have some limited transmission range, you basically get some local neighborhood or distance information which you can use for localization, for example. In addition, these sensor nodes can provide additional information, their information processing capabilities, so diagnostic information, for example. And last but not least, you reduce the installation effort, not only because of this lack of wiring, but also because these sensor networks have some kind of some degree of intelligence which helps with can support the installation process. and make it more automatic. So how does such a system look like? I already told you about these components which are typically on board. So the energy supply are batteries or supercaps usually, and in addition you may do some energy harvesting from the environment using, for example, solar cells, some wind energy solutions, of course small ones, typically here. Vibration can be used, or you use temperature differences, or harvesting temperature differences with material elements. The transceiver module typically uses technologies like GSM and GPRS, wireless LAN. If you are interested in more low power solutions, then you will go for Bluetooth, for example, or this 802.15.4, which is especially designed for low power sensor networks. And based on these sensors, there have been developed extended protocols like Zigbee and wireless HART, which not just include the physical layer, but also some networking capabilities. By the way, what you see here is something which we have analyzed in a recent project with a master student. This is a solution with 4 antennas. You only see 2 directional antennas, the other ones are on board, and where we have analyzed neighborhood discovery protocols for such a solution. Now, the microprocessor, a typical example is here, Texas Instruments SP430, which is a pretty low power processor, typically consumes something like below 10 milliwatts, as far as I remember. In active mode, and very low consumption if it is in a low power mode, in the range of, I think, microwatts, 10 microwatts roughly. So the requirement is that they have to be low power, and the tasks they are performing is some coordination of these modules, energy management, typically also application management, and information processing. And then there are some sensor modules. These typically integrate the input of several sensors. Examples are temperature, humidity, acceleration, vibration, gas concentration. But this is, of course, not a complete list. Now, what are the main requirements for large wireless sensor actuator networks? Well, first of all, you want to have a long lifetime. This is important because you have not a permanent power supply here. So this implies that you have to use low power hardware, first of all. You possibly also have to use energy harvesting to get additional energy input. But either you are able to supply the system purely from energy harvesting, which would be perfect, or you have to support or prolong the lifetime of a battery, for example. Very important in these, or typically in these systems, is also that they are operated in some kind of mode where they most of the time sleep and only for certain purposes wake up to provide, for example, some information, measurement or exchange with neighbors. And a very useful solution, which is getting more and more competitive now, are wake-up receivers, which means that you have a very specialized receiver, very low power receiver, which is only there to wake the system up. So you provide a signal only to this receiver, wake the system up, then this signal wakes up the remaining components of this platform, and then you can do your normal communication tasks. In particular, actually, most of the energy is consumed, at least nowadays, by the transceiver, much more than by the processor. As such, it makes sense to do some information processing locally and inside the network, and not just communicate over data. Another requirement, very important one, is low installation maintenance effort. This requires some solutions for example, self-diagnosis or self-organization. I will give some examples later on. And last but not least, there are at least some information which have to be transmitted reliably in fast to some control center, for example. An example are for alarm transmissions. there are solutions for this. I will not go into detail for this. And very helpful in this for this aspect is also, for example, this wake up receiver. Now I have already told you that distributed information processing makes sense. So here I give you some arguments why. I told you already that you could, of course, or typically you just collect raw data currently and process them in some central instance. But the problem with these kind of networks is that the communication load of the sensors close to the gateway increases dramatically if the sensor network is large. And the consequence is that these loads then determine the lifetime of the whole network. So you better think first and then communicate only the information which is necessary, not the raw data. Another argument is that this distributed intelligence also supports some self-organization properties, which makes these networks more robust. Examples are that these sensors and actuators coordinate, for example, some common time, which you definitely need in order to timestamp your events, and also to coordinate the activities. For example, they cannot communicate all at the same time, at least not on the same channel. So this has to be coordinated, and this requires some temporal coordination. Also, therefore, you need some common understanding of time in these networks, which is not trivial. You may also know some information about where is this node, so you need some common understanding of a coordinate system, special coordinate system. You have to control, as already mentioned, medium access, and of course also routing, which makes them much more independent from a central coordinator. And we have developed several prototypes which really show some kind of plug-and-play feature. Another argument is that with these features you can reduce costs because you can reduce the amount of central powerful processors or controllers and routers which are needed. Another argument why distributed intelligence will come in the future is basically Moore's law in a certain variant. So, for example, Intel claims that they want to reduce the energy consumption of processors by a factor of 100 to 2 picojoule per floating operation until 2018, which means that for the same energy we can do a lot more operations locally, which is also in favor of distributed intelligence and local information processing. Last but not least, and this is pretty much related to what you're doing here, the trend towards specialized hardware, in particular neural hardware, where new processor architectures have, for example, specialized cores. And among these specialized cores are also neural network analog cores, which are especially suited for applications like, for example, pattern recognition, classification, or forecast. And they are not programmed in the traditional way, but typically trained. So this is a little bit different, but also of an advantage because you can do it online. So you can basically learn doing operation. Now, some examples for self-organization I already mentioned. These are as time synchronization. So the typical solution is that you exchange timestamps with neighboring nodes, timestamps which tell you, which basically reflect your own estimate of the closing network time, and by some kind of consensus like protocol, or typically for synchronization processes, these converge to, typically at least under certain conditions, converge to a common synchronized state. And we have set up a prototype which actually reaches with this and a bit more algorithmic insight to compensate for example, differences in time of frequencies of drifts. You reach an accuracy in the range of the time interval, which in our case we have a 32 kilohertz timer. So this means you reach accuracy, synchronization accuracy in the range of 30 to, let's say, 100 microseconds, which is the limit you can reach with this kind of hardware. Of course, if you use timer with a higher frequency, you can reach better values. And this solution also has the great advantage that the synchronization error is almost independent of the distance between the sensor nodes, typically. Which is different to a kind of master-slave synchronization protocol where you typically have errors which grow the further the distance, the height distance between these nodes is, and which require some specific compensation algorithms. Another example is channel allocation. As already mentioned, these sensor nodes have to use different frequencies or time slots for communication, whatever you use as channels. Well, this can be done by some very simple protocols, but you have to keep in mind that this is basically a graph coloring problem. So, which means that if you provide the minimum set of colors which is needed, you may the solution of the problem or convergence may last arbitrarily long. So you have to provide enough channels. Of course, you don't want to provide too much because this is a waste finally. We have analyzed this and found some rough estimate, which is a good compromise between conversion speed of this process and, on the other hand, not wasting too much bandwidth. And finally, routing in these networks, you have to select the routes to forward the data, and you can just do this by simply local interaction of these nodes. And ideally, you can also optimize the scheduling to reduce latencies, which is important if you have to transmit information very fast to the collection point. Some examples for network information processing, I already mentioned localization. So in one of our solutions, this works in such a way that these nodes determine their own position in the network coordinate system by just for the moment local distance measurements with their neighboring nodes, and exchange their position estimates with their neighbors. And then again, in some kind of similar to consensus protocols, slightly different. The whole network agrees on a common coordinate system. You have to be a bit careful because whether this really converges properly depends on the topology of this network. If you have some kind of weak links, where you have, for example, clusters which are linked by only one or maybe two links to the other cluster, then you may get inconsistencies. But this is does not depend on the solution. This is a principal problem because you have not enough.
How do you measure the local distance? By the time it takes the signal
This depends on the technology. I already mentioned here two. So field strength, for example, is very simple. It's quite basically for free because anyhow you have to communicate and you measure the signal strength.
So you measure how weak is the signal.
Exactly. So you have a model how the signal attenuates with distance. This gives you basically a distance estimate, but this is very poor measurement. Actually, nevertheless, for many purposes, it's enough. What it can reach, we get an accuracy of 2 to 20 meters, depends on the topology and the system and the distances. So this is okay for many applications. For example, for this navigation purpose, it's okay until you reach locally the area where the material is. In order to find the material precisely, then actually in our solution we switch to a kind of to a different kind of navigation system, which actually uses directional information, but works only locally. And the last solution is that the material either blinks or produces some sound for the last meter, maybe. Not the last mile, the last meter. And other technologies like ultra-wideband also provide the opportunity to use some kind of time of flight information. And then this is much more accurate. And with this technology, you typically, with the current technology, you reach accuracy in the order of 10 centimeters roughly. And the last example for network information processing is distributed inference. So the general task is to infer unknown variables from observed variables. So in this example, the nodes determine unobserved variables through an exchange of information. And this information is based on local observations, so local measurements, for example, and information which they have already received from neighbors. And an example which we have implemented is pattern matching for diagnosis. So you can imagine you have several of the sensors measuring light, and they decide locally whether this is bright or dark. So you have, in a very simple case, just a binary measurement in this case. And then you can imagine that you have some patterns of bright, dark values which you want to recognize, and you want to say, well, is this pattern 1, 2, 3, 4? And we've implemented such a solution together with the other solutions for time synchronization, channel allocation, or routing was not needed in this case. This just uses broadcast. And the effect is that with this solution you can, all the nodes after some iterations, know which pattern is active currently in the network, or very likely. They even provide probabilities for this pattern, given the current measurements of all sensors. Of course, you could also collect the data, but as I already mentioned, the problem is that then you have unevenly distributed communication load on these nodes, and you first have to collect, process, and then redistribute. So what are the challenges which we are facing mainly? Well, first of all, we have to do some standardization for these purposes, unfortunately, because interoperability is an important customer requirement. To provide a solution is very easy, but to get the solution accepted is not so easy, unfortunately. So we will very likely have at least an extension of existing standards. There are also challenges concerning automation architectures, future automation architectures. Well, first of all, the increasing computational power of these field devices reduces the need for routers and controllers. This definitely will also have some impact on, for example, the business of Siemens. So Siemens is selling automation, components for automation, like controllers and so on. Then the Internet protocol will very likely enter the field device level, which is very welcomed by the automation people, because they already know this protocol from their Wi-Fi installations, and we welcome if this could also be used at this field device level. And in the meantime, these protocols are really concerning the energy consumption efficient enough to be implemented. As already mentioned, as you have more distributed intelligence, you need less hierarchies in these automation architectures. So this means that the engineers have to probably learn something new in this respect, and very important, if you want to have some unique selling propositions, then very likely these are optimal self-organization and efficient network information processing. As such, this is very important. So this was a kind of overview on this wireless sensor network topic, to show you what are the trends, what are the challenges. And one of them was, of course, this network information processing. This is also a topic which is very much related to your research. Therefore, I would like to focus on one special solution which we developed some years ago, which is a special version of recurrent networks, which are, or at least at the time when we developed this, have very useful properties concerning application in embedded systems. So, just to give you an idea of where the solution can be located compared to other approaches. This kind of state-of-the-art collection is of course not complete, but shows you the main approaches roughly. So the original recurrent neural network topology was introduced by Ellman, and this basically has an input layer, a hidden layer, and an output layer in its simplest version, and the hidden layer has a recurrent connection. It's fully connected, and everything can be trained. All these weights can be trained. The drawback is that due to the fact that you have no constraints on these recurrent connections, training can lead you to a dynamically unstable system, and you have almost no chance by this online training to get out of this region, typically at least, without additional measures to be taken, of course. And the second one we were looking at was this echo-state recurrent neural network, which is one example of these reservoir computing approaches. The topology is basically the same as the Ellman network, except for the fact that the input and the recurrent layer weights are not trained but kept fixed and chosen basically randomly. The only constraint is that they are rescaled in such a way that the response of this hidden layer is basically transient, so it's stable, dynamically stable in that sense. The drawback is that due to the fact that you're not training this, but basically creating a random reservoir with this construction, where you select basically by training this output layer, you select the proper reservoir responses. You need a large recurrent layer, and in some applications at least we observed poor generalization properties. One approach which tried to avoid these problems was the block diagonal recurrent neural network, which splits the recurrent layer into 2x2 blocks, or two neurons coupled to each other. So the recurrent weight matrix is a 2x2 block, and the instabilities are avoided by using parameterization. Basically, this is a kind of extended oscillator, and you can imagine that you can constrain the weights in such a way that it always is stable in the sense of its eigenvalues. The drawback is that you also need a large recurrent layer in order to get sufficient modeling power. Now, so if you want to have a solution for embedded systems, then first of all, this has to be a compact solution. So we cannot use too many hidden neurons, otherwise we run into problems with this limited computational power which we have. And on the other hand, imagine that in these sensor networks, for example, the solution has to run autonomously for a very long time, so it has to be robust and stable. So for this purpose, we were looking at a solution which hopefully unifies all these useful properties of these solutions. And the solution we found was called Spiral Recurrent Neural Network. So it's basically the same, from topology, the same solution as you've seen before, except that this recurrent hidden layer has a special structure. It's actually a circular matrix, which means that in each off-diagonal or case off-diagonal, you have basically always the same values. And if you plot your recurrent neurons in a ring topology, and then this means that, for example, the next nearest neighbors in some in this clockwise order, basically these couplings are all the same from here to here, from here to here, and similarly for the second next neighbors, and so on and so on and so on. If you raise this topology, then you can imagine where the name spiral comes from. So well, this is the first step, but this does not guarantee stability. But if you parameterize these beta values in such a way, which is no restriction on the values of these betas, then there is an estimate on the eigenvalues of this matrix, which says that they are basically smaller than the sum of the absolute values of these betas. And with this parameterization, you can further reduce this to the simple statement, which basically means that by choosing a suitable gamma, you can guarantee the stability of this recurrent system. And the topologies we have looked at was actually to use more of these spiral recurrent neural network blocks here and couple it one or more and couple them to some outputs and of course inputs on this. So the training was another challenge, and we have first, our approach was actually to start with some probabilistic approach, some kind of Bayesian approach, looking at the probability for the weights at time t given the observations until time t. And well, so far this here is exact. There is no approximation. But then, of course, in order to do this, to simplify this, you need some simplifying approximations. For example, the assumption is that the weights, the probability or distribution of the weights given the observations is a normal distribution centered around some mean value and with some covariance matrix. This can be, of course, criticized. Probably, this is in practice, this is a more complicated distribution. But on the other hand, we are only interested in one particular set of parameters at the end. So, as such, it's legal. The drawback is, of course, that it may run into a local optimum in the worst case. But otherwise, the solution would become much more complicated. And we have to consider, for example, superposition of such Gaussians. Well, this requirement here is probably less. This approximation is less critical. So, how does the distribution change? The distribution of the conditional distribution of the weights change given the previous weight? Well, to assume that this is some normal distribution which produces some spreading in the distribution probably makes sense. The most critical one is probably this one where you estimate the distribution of the state, the hidden states, given the weights, the hidden states given the weights and the previous observations. And here the critical point is that in principle, with this approximation, because this is given the current weights, we basically have to look at this iteration of steps computed with the current weight matrix. Well, this would imply that you have to redo the whole history with the new weights, which is impossible. Therefore, you have to make an approximation here and replace this by the previous hidden weight and so on and so on in this previous iteration. Then you can solve this in an iterative way. Well, this is basically the measurement distribution, which is very often assumed to be a normal distribution, which typically makes sense as well. So what you end up with is finally, not unsurprisingly, a Kalman filter with a real-time recurrent learning gradient solution, which is basically here. This is the approximation related to this problem here. And well, we have evaluated this solution and found very good performance. So these are errors on a logarithmic scale. So the first test was a spike time series with period 21, just one example, where we all networks were of the same size in the sense of trainable weights. So this means computationally comparable. And because the training is actually the most computationally expensive process in this game. And what you see is here that if we were comparing the solution with the one, so L1 networks, so standard recurrent neural networks with block diagonals, echo-state neural networks in our solution, and you see that the error goes down pretty well with our solution. Well, the fact that the L1 network is better here is not a surprise because it has more computational power, but you have to be careful with this statement because this data here take into account only those runs which terminated in a stable way. So we had some runs where simply had problems and run into some unstable regime. So we discarded these measurements. So this has to be taken with some caveat. So similarly, for another system where we have used the lowest time series as a target and try to predict it, and so what you get is here this kind of comparison. So here, block diagonal networks, our solution, and also the other network were pretty similar at the end. Only echo-state networks had some problems. And in the magic last time series, we have seen quite some advantage for our solution. Another example which did not use artificial time series, but manually created ones, was this can be very simple example. So you basically use your computer mouse and create some figures. We have chosen as one of the simplest figures this 8, line 8 figure, or infinity symbol if you want. The reason is that at this crossing point, you really have to have some memory. You need some memory in order to predict what to do next. So go this or this direction, because the position is of course known already, but the position information is not enough. You have to have more information. And you see that in this example here, after 13 training examples, so 13 times running this 8 with the mouse, the system has already learned enough to repeat this pattern, of course with some error, but quite reasonable way. So another application was conditional prediction. So typically you don't have time series which correspond to some stationary process very often. This is, I think, more or less the standard in practice. But rather it's a sequence of process states. So here are some simple examples. So traffic on roads can be very good predicted if you have just considered some line segments, some street segments. Once there's a crossing, you have problems because it's very difficult to predict how much traffic turns right, left, straight without additional information. So basically, you can predict, let's say, from how the traffic changes on a certain road segment, but not when it turns into another crossing. Or other example, if you open a valve in a pipeline, for example, then this induces predictable oscillations in the flowing medium, for example, but it depends on the status of the valve. So if you have this information on the status of the valve, you can predict these oscillations or the wave pattern of the valve, or the other way around. If you observe these patterns, you can say, well, what was probably very likely the status of the valve. So the solution for training a recurrent neural network, which we have used, is that we add simply an additional trigger signal indicating a new pattern. So this trigger signal must be unique for each pattern, and we have chosen a trigger signal which is kept constant as a constant input during this pattern. The advantage is that with this solution, the additional constant input separates these different pattern trajectories in the recurrent layer state. So you can imagine that your high dimensional recurrent layer state. For this pattern, typically when this is some subspace, for example, in three-dimensional space, it covers some kind of curve in some area. If you have a similar pattern, or if you try another pattern, you probably will have some overlay of this and destroy this information. So with this additional pattern, you simply shift, give an offset in the space, and shift the internal state to some area which was not occupied so far. So you can store this additional pattern much easier than without this additional input. The advantage of the solution is that by just providing this trigger signal as input, you can replay the sequence. So here is an example. So we were looking at warehouse logistics application. So imagine this is some kind of warehouse. Here you have some kind of obstacles. And here are different passes to reach the locations A, B, C, D, E, F. Well, actually, we are looking only at A, B, C, D for this example. And for the only thing which we provide is a signal which separates A, B, C, and D. So a different constant input value. Choose the value are different. And it was kept constant. And we trained the network to basically replay these trajectories here. Yeah? From this entrance to ABCD. And here you see the solutions. And obviously, recall that these are only replayed based on this input trigger signal, which is different for these four trajectories, but constant over the whole sequence. You see that the system was able to replay this trajectory fairly well with some small errors, but the main point is, in particular, if you look at C and D, look at this example, to a large extent these trajectories are basically identical, only in the end they split. So it's really interesting that these solutions were able to distinguish these two trajectories, because this part here is basically the same. There are different scales here, shifted. Now we were also looking at the storage capacity of these solutions. So the question is, how many temporal patterns of a given length can you store and retrieve reliably? So we did some analysis with increasing the number of hidden nodes, and with two patterns types. So one pattern had 6 time steps, and the other patterns had 11 time steps. We created them randomly and trained the networks with 50 presentations of each pattern, and training was considered successful if at least 1 out of 30 trials yields a root square of below 0.05. And what we found is basically a linear relationship between the number of trajectory patterns to be stored compared to the number of hidden nodes. As you can see, the slope here is different for the two patterns. Well, roughly factor of half reflecting the increase in pattern length. But well, this is really a linear relationship, has to be investigated with more examples.
Why do you require less nodes to distinguish longer patterns?
No.
No, you distinguish less patterns.
No. With the same, but this is the same number of space. You can store less pattern here.
Yeah.
Less pattern.
Yeah.
I see.
Okay, so to summarize these solutions, the Spiral Recurrent Neural Networks, so we're able to combine the dynamic stability of for example, the Echo state recurrent neural network with the modeling power of the Elmer network, which is very suitable for online training. We have provided a robust, reliable, and fast online learning of time series based on this extended Kalman filter and recurrent learning training or combination. Typically, we observe good generalization due to trainable recurrent weights. And we observe that the storage capacity grows linearly with the number of figures in the current hidden layer, similarly as you know it for the output network, for example. So this is not a surprise as such. I would like to mention that with this solution we have won a competition at the World Congress of Computational Intelligence 2008, I think, where the task was to predict the filling level of, how do you call it, now these cache systems. Forgot the English word. Geldautomaten. It doesn't matter. Yeah, exactly. We have built very sophisticated solutions based on huge networks and a lot of tuning effort. Well, if you look at the results, I don't know whether they're still existing. We're probably ranked 2 or 3 because there were some proposals submitted, but the people did not show up at the conference, so they had to give us the award. But nevertheless, I mean, this is very simple, and as far as I know, the only online learning approach which we used. Nevertheless, we had very good performance, so we were pretty close to the best solutions, and better than the solution which was used so far. Such an interesting result. Well, and finally, with a conditional prediction, simply with an additional trigger signal indicating new temporal pattern, this improves the learning of more pattern in the network. Because otherwise you may destroy the information, the previously learned information to some degree, which you probably have already observed in investigations. So as such, this was suitable for implementation, and we already tried to implement this on our sensor platform. So we did succeed, but the size is very limited. So we can implement only a system with, let's say, well, it depends whether you implement online learning or not. You need not, but then you have to train it offline. So without the online learning, you can implement quite reasonable sized networks where you can model quite interesting temporal features or trajectories. While with online learning, you're limited to maybe at most, I think, 5 hidden neurons, which gives you a limited modeling capability. Because the training is the biggest effort at the moment, because in some sense you have to invert the matrix, and this is expensive. Yeah, so this still limits the application of the solution with a given hardware. This will improve in the future. And but this is also the motivation for me to take a closer look at your solutions here, because they provide a way out of this restriction. And yeah, this remark I would like to thank you for your attention, and I guess we will have some questions.
Thanks a lot for that very interesting overview. The session is open for questions and discussions.
I am very interested in this online learning concept, but I don't know how it works. I mean, you think of an application, you let the network to learn. Can the goal to be changed on the fly? I want this set of sensors to change. Is the system able to learn again, or is just one time? Just learning for one specific purpose.
One typical example of learning is, for example, prediction. You want to predict sensor values, for example. So depending on how you're training, you can train for the next sample or for a couple of samples. So it doesn't matter very much. It gives just a different target, but let's assume we want to predict the next target, the next sensor machine. So the network makes a prediction. So you compare the actual value with the prediction. Then you run this algorithm to adapt the weights, and as such, of course, you can learn even if the model changes in principle. Now, if you have a stationary process in the sense that this is one process which generates this series, then this will be learned with this solution. If this process is changing, then it depends how it is, how it changes. So if it's temporarily changing slowly, then you can probably track it with the solution, depending on how fast this changes in the parameter space, basically. If it's faster, for example, a sudden change, then you need some time until this has been relearned, but then you may have forgotten the previous solution. If you want to keep this information, then you need the solution with this additional trigger signal, at least, or something similar, which somehow saves the old information associated with the additional trigger signal, but then you need a kind of trigger signal which gives you a hint that the situation has changed.
This trigger signal, did you extract this from basically your network responses, or was this support?
So far not. This would be the kind of next step. We introduced this manually. So this was not learned.
I would also be interested in the similar thing, having the trigger signals there when there's a new pattern detected, as you said. But what qualifies a new pattern? I mean, I guess this only applies to cases where you have a very limited number of already learned patterns. And then otherwise I would ask myself how approximability when this kicks in actually, and then your new pattern is actually not recognized as a new pattern but as wrongly as an old pattern.
Your question addresses the problem how to learn this trigger signal, basically. This is something which we have not solved with this approach so far, because we have provided the signal manually from external source. This was, but there are many examples where you can provide this. The example which I showed, this warehouse problem. So imagine that you, so for navigation purposes, for example, you know where you are, this is your entrance, and you know where you want to go. So the starting location and the goal determines your trigger signal. So you have, for example, a database where you store these trigger signals for these different starting point and target locations, and then after this training, the system is able, just with this input, to find proper trajectory, and then this can be used for navigation purposes, for example. Another example was this valve, so this pipeline flow example. So there you basically have the position of the valve as a trigger signal, as an external one, so you don't have to learn it. It's usually it's available. The challenging task is if you only observe some trajectories and want to detect, well, has the time series or the process changed suddenly or not? In some cases, this is probably very difficult to change because you know time series which have a standard process. Just take this chaotic time series, it can be very quiet for some time and then suddenly became fluctuating very violently. So, how do you say where is a new process starting? Yeah. So this is a very challenging task. Therefore, we have avoided this so far. That's very interesting. Maybe it also makes sense to model these kind of processes automatically, in the sense that you say, okay, these kind of time series has some typical pattern, and I just want to classify this as one process. And then when it suddenly changes, irrespective of whether this is a different process or not, I say, okay, this is another process, and try to cluster these kind of systems. Then I can use the cluster information as a trigger signal, for example. This is an option, but we have not analyzed this so far.
And a question related to this stability of training. You mentioned the AND networks, they usually suffer from instability in training. I might say, certainly the AND network is actually the one which might be closest to what actually is implemented in our brains, right, with plasticity mechanisms.
Well, I think there are also some mechanisms to control it.
That was my question. What prevents, for example, the instabilities to turn up in the brain, and can this be helpful for training?
Well, as far as I know, there's some limitation on the average activity of the brain. So if there's too much activity, then there's some inhibition. For example. As far as I know this, but you have to ask some neuroscientists
But people haven't tried to implement such features in the element training procedures.
This is basically a related approach is this weight penalty term, which is introduced. But for me, this weight penalty term is has some drawbacks because it tries to keep the weights low, and you have. It's difficult to estimate the weight of this term, this penalty term. So the most appropriate way to control the behavior of the network is to parameterize the hidden layer in a way which guarantees that it does not become unstable for our purposes. But there are definitely other solutions which might be useful. I mean, the difference between the brain and this system is that the brain is much bigger, so you can use you can take advantage of statistical effects, which we do not, which we cannot do in the smaller networks.
If there's no more questions, let's thank the speaker again. Sollacher will still be here this afternoon, so if somebody is interested to meet him